Swayam Prabha. Digital India. Educated India.
So welcome to this next talk. So we'll be talking about virtualization. I'll go into slideshow mode. I hope you can see it. So you can stop me whenever you want, so that uh, we can have a discussion where required. Uh, I don't want it to be a monologue. I think this should take around an hour and 15 minutes or so is my estimate, but um, I'll try to go slow so that if there are questions I can handle them, and then we can cover the remainder in the afternoon session, as we have a pretty short demo session. I think it will be more of a thing where you need to go back and do things rather than doing a lot during the actual demo. So let's get started. So I call this Hypervisor as the Lord of the Rings. I think you'll get an idea of why that is as we go further into the talk. So you have, I think in the previous week, you've covered quite a bit of the operating systems and uh, the architecture of operating systems. So, and some of the processors, ISA and things like that. So I think virtualization is a very good example of application of some of those ideas and concepts which you have learned during the uh, first week. And I hope you'll be able to relate to some of the things from your previous week as you start understanding about how hypervisors work and how processors are virtualized. So the agenda for this talk today, I'll start with, it's more like a history session rather than a technological session, in my opinion. I think it's a history of virtualization. So you will see how it has gradually developed over the years. I think it's a pretty old technology, and also I would like to say, actually, I don't really consider technology as old or new. I think um, technology keeps coming back in different ways. I think a lot of the old, what we called as old technology, keeps coming back as in new forms. So I think it's basically good technology. I think so. I think you should try to understand how things work so that you'll be able to apply it to new problems as you see them. So I think that's what you will see has been happening through the history of computer science, I think. So what I thought today is I'll start with the origin of hypervisors, give a historical perspective of that, how things started. We'll talk about VMM architecture. So VMM stands for Virtual Machine Monitor. So we'll talk of architectures and the criteria for a processor to be virtualizable. We'll look at x86 virtualization. I think you've covered a bit of the Spark processor in the previous week. So it will be good to cover some of the x86 processor basics before we get into what are the challenges which we see from a virtualization perspective on x86 processors. And then we will look also at what are the techniques to solve some of these problems which are there on x86 processors in terms of virtualization. So we have multiple techniques for software virtualization, like binary translation and para virtualization, and even that is for CPU virtualization. And then you similarly on memory and IO, you will see different techniques which were used on the software side to solve problems. And I'm assuming that all this will probably finish in the first session, and depending on how it goes, we will probably have the second session in the afternoon, or we can continue if there is time right now, where we'll talk about more of the hardware techniques for virtualization. I think some of the support which has come from the CPU vendors, and then some of the industry bodies around IO virtualization, also from PCI SIG and others. So we'll talk about that and close with that. Finally, we'll have future trends. I think this will just probably be a brief brief discussion. I think you will see more of that tomorrow when Raman talks about containers. I think that's probably what we see as a current trend in virtualization, if I may call it. And then we'll have Rashi, who will help us with the demo hands-on lab with Quemo, and that will give you insights on what has been presented, and then it will also give you things to look at as you go back and try to understand more of virtualization and how it works. So this is what we'll cover today. So let's start with the first section. Um, Before that, I think just kind of aside, I think you will see that I use a lot of Calvin and Hobbes in my presentations. I feel a lot of the Calvin and Hobbes cartoons relate very nicely to technology, especially virtualization technology. And um, I feel if Calvin had been a real character, probably he would have been a computer science geek. Is the way I see it. So uh, I hope you'll enjoy some of these kind of things which will take us off track, but at the same time, it's kind of relevant to what is the presentation. So a brief history lesson. I think virtualization, as I said, is not really a new technology. It's a pretty old one. It started probably in the 60s, even when we had the IBM mainframes. And the reason why it was happening on it was considered a good solution on the IBM mainframes was because the mainframes were pretty expensive, and they were single user systems. So I think the operating systems which used to run on that, I think, were single user operating systems. So I think CMS is one of those which is shown in this figure. And because they were single user, I think if multiple users wanted to use it at the same time, I think it was not possible unless you did virtualization. So that was kind of the need for virtualization, which drove virtualization in that era. And so you'll see that the IBM mainframes had pretty good advanced classical kind of virtualization which was there. So they had a hypervisor which was called the control program, which used to run on these mainframes, and then you had these multiple operating systems, and they were typically single user operating systems. So anybody could run on one of these operating systems and get their isolation which they wanted, and they could get their independence in terms of running their app. So after that, I think it kind of the virtualization went into a kind of hibernation. I think once we saw the era of Intel processors and things like that, I think it kind of went into the back burner. I don't think even the Intel architecture, x86 architecture, was designed with virtualization in mind, and which is why we probably had a lot of the challenges which we saw later with the x86 architecture. And so yeah, like I said, nobody thought about virtualization for probably a long time, and especially because the operating systems which came during that period, like Linux and Windows, were multi-user. So you could have multiple users on a single hardware, and the hardware was cheap. So you had the era of PCs. So the hardware became cheaper than the mainframes, and so you really didn't see a need for virtualization for a long period of time. But then around 1996, I think there was a Stanford research project which was actually funded by the US ARPA, I think the defense agency or somebody. And then the folks who were doing the research were Edward Bourguignon and Mendel Rosenblum, and they later were the founders of VMware. Or at least the technologists behind it. And so they started what was called the Disco project. So the Disco project was trying to do virtualization on what was called the server was called Flash. It was a NUMA system with MIPS R1000 CPUs, and the idea was to virtualize that system. But by the time they finished the project, actually they didn't have the hardware ready. And so interestingly, they actually developed their Disco hypervisor on top of a simulated OS called SimOS. So it was running on top of a simulator, and not really a real hardware. So it was pretty interesting. I think multiple levels of interaction in a sense. So, and the reason, I think, like I said, it started getting popular in 1996, I think, even though we had multi-user operating systems, was the fact that we were getting into this era of multi-core systems. So I think Moore's law was kind of hitting some kind of bottlenecks, and so the way to solve the issue was to probably have multiple cores on a system. And once we had these multiple cores on a system, we had a lot of CPU processes, CPU resources, and how to kind of virtualize them and be able to share them among multiple users became a challenge. And that is when we started seeing more of these virtualization technologies coming back. So we had VMware, which started in around 1999, again, like I said, by Mendel Rosenblum and others who had been involved in the earlier Disco project. And they came out with the first release was called the VMware Workstation. And then they came out with a server product, which is the more popular ESXi, which we know of today. And their hypervisor was supported both on both Intel and the AMD x86 servers. So to go further back in time, I think Popek and Goldberg. So this is one of the signature papers, the classical papers on virtualization. So you can see the reference below in Communications of the ACM back in 1974. So this is like the Bible of virtualization, and it's probably what has inspired people. And also, if you see papers even recently, they will refer to the criteria laid out by Popek and Goldberg in the original seminal paper in 1974. So it's an interesting paper. I think there's a lot of mathematics in it. So I think if you have an interest in that kind of work, I think you should go back and read the paper and what it talks about from a mathematics and theory perspective. But to kind of summarize it at a high level, I think they said that the requirements to do virtualization on a processor was that it had to be efficient. So you could have most of the instructions execute directly on the hardware. You needed resource control. So basically the executed programs should not be able to affect the system resources, and the VMM should be in control of the resources. And finally, equivalence, which is the fact that if you run a program on a bare native system versus under a VMM, you should kind of get the same behavior when executing on both of them. So these were kind of the main things which they came up with. They also, I think, came up with the concept of what is known as the classic, now we call as classical virtualization, which is basically trap and emulate kind of virtualization. And it's in similar concept to what you've read last week with, or heard last week with operating systems, where we have a kernel and we have a user space program. And so you have a trap and emulate architecture where a user space program, if it wants resources, which it needs access to, which are system resources, then it needs to trap into the kernel, and the kernel needs to be the one kind of doing the work on behalf of the user space program. So we have a similar next level of layer, if you can call it, with virtualization, where even if the OS kernel needs to get something, then it needs to trap into something like a VMM, and the VMM needs to emulate the actual resource request. So Popek and Goldberg, I think they came out with what are the virtualization requiremements from a processor perspective. And they said that the instructions of an ISA could be classified into basically three types. So one is privileged instructions, basically instructions which need to be only executed by a privileged user and in a privileged mode. And we'll talk more about that later. And then there are control sensitive instructions, basically where you're trying to change the state of the system in some way, or the processor. Then those are control sensitive instructions. And third there are behavior sensitive instructions, that is the instructions which depend on the state or the mode of the system when they are executed. So they can give different results based on whether they are run in a higher privileged mode or a lower privileged mode. So Popek and Goldberg basically classified these three levels of instructions as important to a kind of virtualization happening on the processor. And virtualization, the platform needed to take care that these were handled in a very effective manner. Okay, so again, like I said, I think in the 90s and late 2000, I think we started early 2000, we started seeing more of these virtualization technologies coming in. So from an enterprise perspective, I think what we saw is that we had Initially, before we had virtualization, we had something called partitioning. So partitioning would basically involve dividing a node into multiple entities. So instead of actually virtualizing the layers, it would be the basic resources of a system. If you take today, for instance, is CPU, memory, and IO. So if you were to partition a system, then you basically are dividing the number of cores, dividing the amount of memory which it has, and dividing the number of IO devices it has, and assigning them at a pretty coarse granularity to a particular operating system. So that was partitioning. So I think HP was, along with Sun and IBM, was a pioneer in the space, and we had the first hardware partitioning technologies from HP. So HP had the Superdome series of platforms starting in around 99, or probably in 2000 timeframe is when the first Superdome came out on the PA-RISC processor. And then we had Superdome versions with Titanium, and then later now we have, even with x86 processors, we have the Superdome series. So the first Superdomes, if you see the picture on the left, is actually how a Superdome looked like. And it was a scale up system. So if you count here, you can see that there are 8 what are known as blades, and each blade is basically a 2-socket server on its own. And it would be 2-socket server, 2 sockets of CPUs. It would have some memory, say 64 GB of memory or something like that, and then it would have IO devices, which was kind of at the back of the system in terms of a backplane where IO was presented, and that was kind of given to each of the blades in some manner. So you had mezzanine cards on each of these blades, which would connect to that IO fabric at the back. So this was a pretty neat architecture, and it was a very well segregated model. So it was natural that each of these 2-socket blades could be made as an independent server, and that was what I think we could support with the Superdome. You could kind of combine them, so you could have maybe 4 of the blades combined together and have one, what was called an NPAR, or a hard partition. Or you could have, like, at a granularity of just a single blade partition. So you could basically mix and match resources, so that based on the customer workload, for instance, if the customer is running an enterprise workload like Oracle, he would need a set of maybe 4 blades for running the database server, which would be a scale up system, and they could use the single blades for their application layer. And so it was a pretty neat architecture, and used a lot by enterprises in that time frame. And even today, you will see banks in India and all who are using SBI, especially, is using the ST2 architecture, and it still continues to do quite well, even though it's become a bit of a legacy with Titanium, and x86 is the one which is the way forward. So Sun similarly had something called dynamic system domains, and but then from hardware partitioning, again, the 2 sockets seemed like it was becoming kind of pretty coarse, right? I think if you see, like I said, with multi-cores coming in, I think even a single socket would have started getting like 8 cores or 16 cores or something like that. And so as the number of cores started growing, the usage of a single blade with 2 sockets was not complete. I mean, you end up using only around 30% of the CPU or something like that. So that's where I think the software firmware partitioning first started. I think both I think HP had a product called Virtual Partitions, which was VPAR, and then IBM had DLPARs during that time, and Sun had logical domains. And all these 3 technologies were kind of partitioning at the firmware level, and they were able to give resources at a much finer granularity. So you could get a single core for a particular operating system to run, and then you could have a amount of memory, let's say 16 GB of memory, and a particular IO card or something like that. You could divide it at a much finer granularity than the blade, which is shown on the figure here. And that was the initial kind of step to solve the problem of having too many resources and not being able to utilize them fully. But then even that, I think at some point people started seeing that they were not able to utilize it fully, and also it became kind of inflexible. If you have a system where you have divided it, let's say in the NPAR case, for instance, if you've divided it into 4 blades as the database, and then you have single blades for the application server. And then for some reason your database needs more CPU, then you can't really change that. I mean, it kind of is stuck at that. Or if you see that the application servers are not really utilizing resources and you would have preferred the database to get more resources, you can't do that with the partitioning model because you are kind of limited by the fixed kind of partitioning which you've already done. So that is when I think people started looking at virtualization again. And we had all these technologies coming through from multiple vendors. HP, and in fact, interestingly, there is a story where HP was working with VMware at that time, around 2004 timeframe, where we were, I think VMware was not even out in the market at that time. And we were working with them, and there was thoughts about kind of working together on the integrity VM product. But I think VMware at one point decided that they wanted to pitch all their efforts into the x86 space rather than Itanium, and so it kind of parted ways. But if you see the original HP Integrity VM architecture and the VMware GSX workstation architecture, you'll see a lot of similarities in the way they were, and that's probably because there was a lot of collaboration and discussions during that period. Uh, at the same time, I think IBM also came out with what was known as SLPARS. So it was shared LPARS. This was more of a firmware virtualization approach, pretty unique in the industry. I think I'm not aware of anyone else. I think Hitachi Virtage was also kind of similar in terms of firmware virtualization, but there are not many people who have done this or attempted this. And in this, the hypervisor layer in the IBM SLPAR case and the Hitachi Virtage case was basically in the system firmware itself and was not really a software entity on top. But then if you see VMware, GSX, Microsoft, Hyper-V, Zen, KVM, and all those others who came later, I think the hypervisor layer was in software and what is traditionally called the VMM. So the VMM and hypervisor are kind of similar, different names for the same technology. So you will see that interchangeably used. So you will see that the hypervisor or VMM layer started being in software around this time frame. And then finally, I think now what you're seeing, in fact, it started quite some time back with HP had a product called HPUX Secure Resource Partitions, where you could actually take a single OS and have resources divided within it. And that gives the maximum flexibility because you can have just a single scheduler which is trying to decide which application needs more resources. So it provides the highest level of flexibility. But then the isolation, if you can see, the isolation kind of goes down as you go from hardware to software partitioning to virtualization to resource virtualization, because now an app which is running can actually impact another app which is running on the same OS if it's in a container. But again, containers are taking off now. I think probably because of the cloud era with the microservices and things like that. So some of these containers are becoming small enough that it makes sense to run them within a single OS instance. The other reason why I think virtualization was more popular earlier was because we had this huge legacy with these monolithic kind of software pieces like databases from Oracle, for instance, or IBM software DB, for instance, which could not be easily ported to a new architecture. And it was easier to do a virtualization where you could adapt the VMM to a particular application's requirements in terms of ISA and things like that. So it was easier to run it virtualized on top of a system if it needed a legacy kind of architecture. But that I think now of late, I think since there are most of the architectures have been x86 and maybe to an extent power, I think they've kind of got localized at least in the enterprise space, and so we don't see that real issue of having to support legacy. And with cloud, I think it's becoming more prevalent that you are seeing some of these container technologies take better shape, and then with things like Kubernetes, which is on top of these layers, it makes it easier to develop these. It makes you not tied to a particular vendor. Also, I think otherwise you'll have some of these vendors like VMware or someone only providing some of the virtualization layers. But with containers, it becomes more open source. It's more open, and multiple players can play in that space, and you get a lot of flexibility. So those are probably the reasons why we are moving to this era of containers, and I think Raman will talk more about that in tomorrow's discussion. Just to end up on that, I think apart from secure resource partitions, we had Solaris containers, which was very popular. They had their zones technology. I think some of those are like now, I think, part of the Linux containers and things like that, and Dockers and other technologies of late. And then there was something called PVC. I forget the full form of it. And then OpenVZ and IBM workload partition. So these were all technologies which were kind of based on a single operating system and being able to virtualize within that. Okay, any questions so far? This is, I think, so far I've basically introduced the need for virtualization, the history of it, I think, in a sense, and like why enterprise, I think, architectures needed virtualization, and what are the kind of the products which we have seen. Okay. So moving ahead, I think so if I go back to Popek, Goldberg and Popek's paper, I think they also came up with this nomenclature of hypervisors. So we had, so they called what is a type 1 VMM hypervisor as one in which the VMM runs directly on top of the hardware. So it's like an operating system, which is the thing which runs on top of the hardware and then virtualizes the resources for each guest, which is it's called a guest. So whatever is the operating system which runs on top of the VMM is basically called a guest operating system in the terminology. And that's a type 1 kind of hypervisor. And examples of it are VMware ESX today is a type 1 hypervisor. Zen is a type 1 hypervisor where it runs directly on the hardware. And then Hyper-V from Microsoft is also runs directly on top of the hardware. It's probably they are leveraged from some of the older operating system. VMware ESX is probably based on, and Zen are based heavily on Linux, I think, and Hyper-V is probably based more on the Windows operating system. But they are independent operating or independent VMMs which do this work. Then there are what are known as type 2 VMM hypervisors. So in this case, the VMM runs inside the host operating system. So it's like a user space process within the operating system, but with some enhanced privileges to be able to virtualize the guest operating systems. So user mode Linux was an example of this. Actually, there is some confusion in these terminologies. I think you will see that what I show as hybrid VMM are also called as type 2 VMMs by a lot of people. So if you come across that, don't be surprised. I think the hybrid VMM terminology is not very popular. I think that it's typically divided just into type 1 and type 2, and some of the hybrid VMM part gets subsumed into the type 2 hypervisors. And why we call it as a hybrid VMMs, as I think, to actually separate the cases like user mode Linux, which is completely in user space, is the fact that in the hybrid case, I think the VMM is kind of sitting alongside the host operating system in some sense. At some points of time, it is the one which is in control of the hardware. At some point of time, the host OS is in control of the hardware. So it is kind of sitting alongside the host OS. And again, the VMM is the one which spawns the guest operating systems in this case. And examples of this are HPVM, VMware Workstation, which was also called GSX, and Microsoft Virtual Server. Probably there are others like VirtualBox and others, which are also kind of type 2 hypervisors. So if you can think of it as just type 1 and type 2, it's fine. I think you don't really need to worry about the hybrid part, but the fact that whether the VMM is completely in control of the hardware versus it is sharing it with an operating system is what kind of makes the difference. So again, so the hosted VM architecture, like I said, the hybrid, which I showed in the previous slide, where the monitor also runs on the operating system on the hardware and is in control of it at some points of time. So the architecture typically looks like this, where you can see both of them. There's a host world and there's a VMM world. Uh, the interaction between them happens to what is known as the VM driver. So there is a driver which has to be installed within the host OS kernel, which the VMM talks to be able to do some of the context switching and things like that. So, and then there is another application in the user space, which is called the VM app, which basically is the guest operating system itself. So the app, as you see it, is called the is also the guest operating system. And on the right hand side, you see the VMM world. So basically, it's a monitor on top of which you run the virtual machine and operating system and the applications on top of that. So these are kind of two different worlds. And again, Calvin and Hobbes, I think, is pretty apt in this case. And in fact, in HPVM case, we actually adopted this terminology of transmogrifier. I mean, we called it transmogrification. We actually called it XMOG instead of transmogrification. So XMOG would be a kind of context switch from a host world to a VM world or a VMM world or vice versa. So I think, like I said, I think Calvin, I think always is relevant. So that kind of concludes the part around what is required from a hypervisor perspective and the history of it. So we'll now delve into the x86 architecture and what it takes to virtualize it and what are the challenges. So if there are any questions, I can take them. Otherwise, I'll move ahead. Okay. So moving ahead, I think so again, a Calvin cartoon to say that I think virtualization is a lot about loopholes. I mean, if you see especially the x86 architecture, I think there are, like I said, and you will see that there are a lot of challenges in virtualizing it. And so, but there are always loopholes. And I think technologists also love the fact that there are loopholes. You know how to solve a problem by taking advantage of some of those loopholes. So I think in that sense, we are like Calvin. So if you look at the basic x86 architecture, I think last week you talked about privilege levels to an extent. I think in the x86 architecture, there are 4 protection rings. And they are kind of concentric in the sense that the level 0 is where the operating system kernel runs. It has the highest privileges. And then you have a level 1 around it and a level 1, 2, and 3 around it at higher privileges as you go into each of these rings, as they are called. And this is why I think you can understand the thing around the title. I think actually maybe I'll come to that a bit more later. It may make more sense at that point. So these are the protection rings which are there. So level 1 and 2 also are operating system services, and level 3 is where the applications run. Level 1 and 2 are typically not used by operating systems. So for instance, a Linux would not use 1 and 2. And I think most of the modern systems, operating systems, don't use it. There are a few OSs like OpenVMS, for instance, and I think maybe a few others who have used multiple levels of these operating system, and they have run some of their services like drivers within level 1 or 2. But it's pretty rare. I think most people most OSs typically use just level 0 and level 3. So each of these levels or these rings is associated with a privilege level, and for a data structure, it has a privilege. There is a privilege level. I mean, there is a in the case of x86 architecture, there are segments. So segments of memory, and each segment of memory has a descriptor associated with it. So whether it is a code segment or a data segment, in which case it will have a privilege called the DPL, which is the descriptor privilege level. And when an application tries to or an OS tries to load a particular segment into the processor, it's basically trying to say that load this descriptor into the register, and so give me access to this particular memory. And someone needs to validate whether the person who's actually trying to do this has the privileges to do it. So that is done through what are known as these privilege levels. So you have a code privilege level, you have or a current privilege level, which is the current code segment register. So whatever is the code running at a particular point of time, it has a privilege level associated with it called the CPL. And then if you're trying to load a data segment selector, you will say that, okay, you will ask for a privilege level, say a requested privilege level, saying I want to load this segment of memory at this privilege level. But then that particular data segment will have its own descriptor called DPL, and it will have a privilege level associated with it. So when you try to load the segment, the RPL has to be checked against the DPL to see if you can really load that segment or not. If you are not allowed to access that particular segment, then it will return as a general protection exception. So that this is basically the how privilege rings and levels and protection rings are implemented in the x86 architecture. And in terms of memory management, I think again you might have covered some of these topics in the last week. But I think the x86 architecture, the way it works is it is a mix of it's actually a sequence of segmentation followed by paging in the original 32-bit architecture. And nowadays, of course, we don't use segments. I think segmentation is kind of um, done away with in the newer way operating systems use it, but it's still there, supported by the processor. So if you see the original architecture of x86 and the way 32-bit architectures were using it, you will see that there are multiple segment registers. So there is a code segment register, there is a data segment registers, there's a stack segment register, there's a FS is I think floating point, and then there's extended, and then there's another GS. So ES and GS are kind of extensions which probably not used too much by operating systems. I think the other four are what are used more typically. So the segment register itself will have a selector associated with it. A selector, you can think of it as an index. So it is basically an index into a. So it also says which. So there is a type of a descriptor table also associated with the segment selector, saying which table to index into. So there are multiple descriptor tables. One is the global descriptor table, and one is a local descriptor table, which is used by applications, and the global one is used by the kernel. So you have a segment selector which kind of indexes into the one of these descriptor tables, and from that you get a basically a segment descriptor. And that segment descriptor has a base address and a limit associated with it. So it will basically say what is this segment, is where does its base start and where does it end in terms of limit. And within that, so any address within that is what is called a linear address. So within that base and limit, whatever address is there, it's called a linear address. And the linear address can be further converted into a physical address by what is called as paging. And paging, I think you looked at last week with the Spark architecture. It's kind of similar. I think even in the x86 architecture, it's not much different. You have what is known as a global register called CR3, which holds the page directory entry. And then each of the addresses is kind of divided like an address. It's a 64-bit address. It's divided into parts where you can go to a directory part of it, or they will index into a page directory. And from there you can point. It's a hierarchical representation where you can point to a page table and then to an actual address in memory. And it's basically it's done so that you can conserve memory. So you have this hierarchical kind of memory management which is done by most of the processor architecture. So I don't think there's probably any of them which does it kind of differently. I think it's very similar architectures adopted by everybody. So in the x86, like I said, you have segmentation, and then you have paging to get to from a logical address, which is what the application sees, to a virtual address, as we call it, to a physical address by going through what is known as a linear address from segmentation, and then to a physical address from paging. So yeah, this slide I think gives you more details of the same thing which I talked about. So you have a segment selector, like I said, which you have the TI part, which basically tells you which is the descriptor table, whether it's a global GDTR or a global descriptor table or a local descriptor table or an interrupt descriptor table. I think there are three of them which are there. And then you have an index which kind of indexes into the table, and then you get the corresponding descriptor, and then you can add it to the so you whenever you try to access a particular memory, you basically say a segment, you say a CS register and colon a particular offset. So you then have to add the offset to get a linear address, and this has to be within the limit which is corresponding to that particular segment. And then, like I said, linear address will get converted into a physical address as required. So the CS as we see it is what we see on the top. We basically just see the index and we see the TI and the requested privilege level. But within the processor, it kind of maintains what is known as the hidden part. So this base and limit, which we are getting it through the descriptor table, is actually cached by the processor. So that's one of the other things which provides a challenge for virtualization. I think, as you'll see later, fact that it is cached within this, and then so if you modify one of these descriptor tables, it doesn't really change the what the processor is seeing. It's still cached there, and you have to have a load or a context switch kind of thing operation which would actually load this. So just changing the value in the descriptor table does not change what the processor sees. So that's like I said, that's going to be another challenge which virtualization will have to handle later. So yeah, I think this is a bit more of a deep dive of paging. Like I said, if you have a 64-bit address, it's divided into multiple parts, and you have a page map level 4, which is from the higher part of the address, and then it points to a page directory, and then so 9 bits. So you can see 9 bits of this correspond to PML4, 9 bits correspond to the PDP pointer, and then 9 bits correspond to the PDE, and 9 bits correspond to the PTE. So you have a hierarchical kind of indexing which is done to finally, and the 12 bytes of the offset are used as an index into the 4 KB page. Of course, this is just with 4 KB pages. You have ways of handling higher large pages like 1 MB, and I think you can go up to 1 MB, I think 20 bits or something like that. So that I won't cover, but you can go through the processor architecture to see how those large pages are also handled. So the basic 4 KB page architecture is handled in this way. And this is with traditional x86 processors. Now I think so this basically supports, actually it's not even 63 64 bits which is supported here. So if you add these, you will see 9 plus 9 plus 9 plus 9 36, and then 12 48. So 48 bits is what we support today. We don't even support greater than that in terms of virtual addresses which are there. So even though you are a 64-bit virtualization, 64-bit system which you're using, you cannot really have 62 to the power of 64 in terms of virtual memory which is supported. It can be only up to 2 power 48 which you can support on the system. So that's something, in case you are not aware, I think that's something interesting. But with the next Itanium, with the next Intel Xeon processor, which is I think called Sapphire Rapids, I think you will see a jump in this. You will see a jump from 48 bit to 57 bits, and you will see another level. So there is now what we are seeing is the 5-level page tables are coming, and operating systems have already added support for it. So you can, for instance, go to the Linux kernel, like Suparna was saying. I think you can go to it and see. You can see how 5-level page tables support has been added there. But in the traditional olden days, it was basically 4. It was even less than this actually. With the 32-bit architecture, you had lesser page tables, and it became 4 levels with the 64-bit architecture.
Hi.
Any question? Yeah.
Yeah. Sorry, I didn't get why we have the 48-bit limit.
It's so 48-bit is the limit because we have 4 levels of page tables. So 2 power 48 is actually a huge amount of memory. I mean, right now most people have not really gone up to those levels of memory usage in terms of system memory usage for a single operating system. So it's a limit which is enforced by the processors today, because we have only these 4 levels of page tables. And imagine a processor also, right? For every address, it has to actually do this translation. So if it has to go to a 5-level page table, it's going to take a lot more time in terms of doing these accesses. So is that worth it if you're actually using only, let's say, 256 GB of memory on a system most of the time? I mean, you probably are wasting these number of cycles on doing this hardware walks, right, within the processor. So you don't really need it. So in that sense, we have always limited it to like 48 bit as the maximum today. But now with the usage of large memory, I think we are seeing terabytes of memories on systems. I think I'll talk more about that in the talk on Friday also. But you will see that there is more memory on a single system now, and so there is more need for this 57 bits, which is what is happening with the next generation.
Yeah, that's very interesting. Can you just tell a bit more how they came to 57 and not 64?
So it's 9, right? Another 9 bits. So it's 9999 36 plus 945 plus 12 57.
Okay, yeah, that's very interesting. Yeah, thank you.
Yeah. Okay. So this itself, you can see the number of 4 KB pages is huge, and I think typically you'll not see systems really using, and this is virtual memory, right? So that's the another thing to understand. This is not really physical memory. So what an application is seeing itself doesn't need to be so huge. I mean, it's the operating system can see probably a large memory, but the application doesn't really need to see that level of that amount of memory. So that's another thing why this is a limit on the virtual address space. There's also actually an interestingly, there's also an limit on the physical address space supported by processors. So in the case of current Xeon processors, I think it's probably 45 bits or something like that. So it's actually much lesser than the virtual address. So if you see, it's one of these PTE entries which finally points to a physical page. This PTE entry, for instance, it is a it's a 64-bit entry which is there, and the 64-bit entry will have some parts of it reserved for the actual address, and some parts of it will have a lot of metadata which is there. So that address which comes out of the page table entry, it's an address of a page. So it's basically, it has to be you have to append the 12 bits to it to get a physical page. But then that supports only around 32 or something like that, I think, today. So it's around 44 bits is something is where the physical addressing stops today, and it doesn't really go beyond that. So that's another thing to be aware of. But I think with the next generation, you will see, I think, 52-bit physical addressing also coming in. So it's kind of growing again.
Yeah, this is definitely very interesting. I have a side question, if you don't mind.
Yeah, sure.
So, do you suspect that Apple's M1 does things differently, especially with their unified memory on chip?
It should be similar. So Apple's M1 is basically an ARM processor, right? So it should have pretty similar in terms of page tables, and it should be doing similar things. I don't know what are the limits for ARM. They're probably not the same as Xeon, but I'm pretty sure they're not really using the full 64 bits.
Sure. Thank you.
Yeah. So this is another interesting paper. So John Scott Robin, I think 1999, I think he wrote an analysis of the Intel Pentium's ability to support a secure VMM. So we saw some of the things which Popek and Goldberg already talked about in terms of being able to trap and emulate VMMs. I think have a trap and emulate classical kind of VMM. And John Scott Robin, I think, analyzed the actual Pentium architecture and came up with a very nice classification of instructions which are called sensitive instructions, which kind of are impacted by the privilege level. And so he classified them into various levels. So 3A1 he called as instructions which reference or change the mode of the processor. 3A2 is which changed the state of the processor. Similarly, sensitive registers, 3B1, which change sensitive registers. So CR0, for instance, is a global register which defines the overall system, the processor, I mean, how it's running, right? It basically defines if paging is on and things like that. And LDTR is the instruction which loads the local descriptor table. E-flags is something which specifies whether what are the flags of the system. I think you talked about some of these things in last week's class also around e-flags and basically whether interrupts are enabled and things like that. So all that comes under the e-flags. So these are all kind of privileged registers, and you should not be able to uh, access them from uh, software which a VMM is running as a guest, right? So I think even if it's an operating system which has traditionally been allowed to use some of these things, it needs to be now kind of handled, because there are multiple operating systems running on the same processor at different points of time, of course. So I think so there are sensitive registers. Similarly, there are sensitive memory locations. So the first part is that you cannot really access all of memory. So if you're using instructions which access memory, you need to make sure that you cannot access all of memory, or only accessing memory which is kind of given to you by the VMM, right? So I think so there are sensitive memory locations. There's a protection system. I think like the privilege level, if you're trying to change, you should not be allowed to unless the VMM is aware of it. So these are all the things which kind of are VMM requirements in terms of the instructions and how they should run. And John Scott Robin, I think, did a full analysis and said that I think why the Intel architecture does not really support a trap and emulate architecture very nicely. The IBM processors, on the other hand, in the mainframe days, they were classically virtualizable. So they had a mode where they could actually support these VMMs within them. But the Intel Pentium architecture was never designed with virtualization in mind, so it could never support these in the initial days. And so some of the challenges from an x86 virtualization perspective, I think I'll go into now, and I think then we'll talk into how these were handled by some of the virtualization, software virtualization and hardware virtualization techniques. So I mean, like now you've learned about operating systems and how they run, right? So you've seen that operating system typically runs at ring 0, which is the highest privilege, and then applications run at ring 3. So even though x86 has 4 rings, 0, 1, 2, 3, it's interesting that they have made it works as that even though 0, 1, 2, 3 can be used in terms of segmentation with all the RPL, DPL kind of checking, which I talked about, it cannot be really used with paging. So if you see a page table entry, which is the last entry in a page table walk, that page table entry has only a single bit saying whether it is user space or whether it is kernel accessible. So it can only support 0 or 3. So that's one challenge which we have with x86 architectures, which means that you cannot really use ring 1 and 2 for running any VMM. That would have been the logical thing to do. I mean, thinking that, okay, maybe you can run the OS in ring 1 or 2, and then 0 can be the VMM. So the Lord of the Rings kind of thing. But that's not possible because of this issue with paging. So like I said, so ring aliasing basically refers to this problem. So you can basically run it as 0 as the VMM, 1 as the OS kernel, and 3 as the OS user space. But then that doesn't work with 64-bit architectures which support paging. And so what you have to do on 64-bit architectures is you have to run the OS kernel also at the same level as the application. So both run at level 3, which becomes a challenge. And because a guest OS can now know its run level, there are a lot of instructions where it can actually find out what level it's running at, and so it will find out that if it's running at level 3, I mean, we don't know what issues are there, I think, in terms of that. But there are other instructions which cause a lot of issues, so we'll come to that also later. So the main problem, like I said, is ring aliasing. The fact that you don't have all the rings available and you have to push the kernel to run at a level which is almost the same as the application which is running in a VMM, under a VMM. And then the second is address space compression. So to do virtualization, the VMM itself needs to use some memory, and it needs to ensure that some of this memory is not really accessible to the guest operating system kernel as well as the guest applications. And so you need to protect that memory. With segmentation, it's kind of possible to support it. I think today I don't think operating systems use the full segment ranges. So I think one way it's done is that you can actually spoof some of the segment descriptors, and the operating system is not really using all the bits which are there, and uh, the VMM can reuse the remainder. With paging also, I think with 64-bit, like I said, I think with the newer architectures, there's no segmentation. So it becomes more of a challenge in that case. But even in that case, I think they found a loophole. So where they found that the most of the operating systems kernels don't use the higher end address spaces. So there are gaps in the virtual address spaces which can be used by VMM. So that's one way that problem was solved. So that's called a problem of address space compression, where the VMM's address spaces have to be protected. The third challenge was non-faulting access to privileged state. So there's a lot of privileged state, like I said, when you're running at ring 0, which the OS kernel has access to. But when it's running under a VMM, it does not have access to those. It's running at ring 3. So, but when it tries to access those, it should not. It should be handled cleanly. So one issue is that it can try to access those, and it can get access to those even though it's running at level 3. So those are some of the challenges which we've seen, and the others are that it doesn't run properly. So both the kind of issues are seen with sensitive instructions on the x86 architecture. The fourth one is the adverse impact on guest system calls. So x86 introduced this lightweight system call mechanism called syscenter and sysexit. The traditional signal system call mechanism was to use an interrupt, the int 80 hex, but then there were these new instructions which were introduced for like lighter weight kind of system calls and being able to make them with lower latency. But syscenter always transits to ring 0, so it works with a traditional operating system. But then if you can imagine a guest operating system trying to make a system call, it will now transition to the VMM instead of the operating system kernel which it intended to. And so that again has to be handled by the operating system, the VMM, and then it has to branch control back to the operating system. So those are some of the challenges which are there from a system call perspective. So a VMM basically has to emulate every guest execution of syscenter 6exit, which can be a huge impact, and then it no longer can be called a lightweight system call. The fifth point, I think, is around interrupt virtualization. So interrupt virtualization is a huge issue, which I think, in fact, I'll talk about later. I think it starts from the CPU, and then there are other things with devices also where you have to be able to manage the interrupts which are coming in, and because the interrupt is coming from a physical device to the system, and then the physical device is, if it's not given directly to a guest operating system, then you have to actually virtualize that, which means every interrupt which is coming from an external peripheral on the system has to be intercepted by the VMM, and then it has to figure out whether this is for the guest operating system. And in the case of type 2 kind of cases where the host is also running on the same system, it has to even figure out which ones are for the host and which one for itself. So those are some of the challenges, and I think when the other challenges from the OS perspective. So when an OS tries to mask or unmask interrupts, then it should every attempt would now the VMM has to be aware, because it has to be able to know when it can deliver an interrupt to a particular guest operating system. So those are challenges with interrupts, and again we'll talk a bit about that later. Um, then I think there are points around access to hidden states. So um, Yeah, like I said, I think I talked about this in the beginning where I talked about segment registers, right? So I think you do not really know what is the um, current value of the segment selector. I think it's cached by the processor. But then if you just go and look at the GDT or the LDT and then look at that particular entry, it could have been changed by someone, but the cacheable part could still be a different part. So all that I think poses another challenge, and you have to actually, the VMM has to maintain this information saying this is the cached state of a particular selector and this is the real state, and then it has to make sure that the cached state is the one which is presented to the operating system rather than the real state. So again, it has to intercept a lot of these calls too. Then there are things around ring compression. So again, I talked about this similar to the ring aliasing thing. I think the fact that you have to now run at 033 kind of model with 64-bit paging, I think that becomes a huge challenge. I think because guest and the OS and the application are running at the same privilege, and it's only the VMM which knows whether it's a guest operating system or a application. And finally, I think a lot of this one of the things with Goldberg and Popex, the requirements of virtualization was, I think they were very clear that the performance should be kind of equivalent. I mean, it should not be like drastically different where performance is really bad with virtualization. So if you try to do virtualization of all these things, all these accesses, I think frequent accesses to privileged resources, it causes a huge impact on the performance. And so early days of virtualization performance, it wasn't unusual to see around 30% or 40% performance impact, even or even more maybe with virtualization. And I think it sometimes defeats the purpose of virtualization, because if you are not really able to use the resources that well, then there's no point of doing virtualization. So this kind of gives a diagrammatic view. This is a lot of it is from that John Scott Robin paper, and you can read that, I think, to get an idea of what are the challenges which each of these instructions. So he's given a very good analysis of each of the instructions and what is the kind of problems that you face with virtualization. So for instance, 3B1 classification, which he showed, which is non-faulting read of privileged registers. So a guest can actually run some of these instructions, and it can get it will not fault, but it will not give uh, either it will not give correct information, or it will kind of give it information which is kind of confusing, because it thinks it's running at privilege level 0, but then it can see that it is running at level 3 by just running some of these instructions. Like SGDT basically is a store of the GDT, and SIDT store of IDT, SLDT store of LDT. So you can do these instructions and actually save these pointers to these descriptors tables to memory. So if it kind of saves it to memory, then it can actually see the descriptor table and see that it's not the real one which it is accessing, because the VMM would have virtualized some of these things. So a lot of these instructions are a challenge. So, and somehow the VMM has to ensure that when OS tries to run some of these instructions, it kind of is able to emulate them. And it can't do it by standard trap and emulate mechanisms, like I said, because it doesn't trap. I mean, these instructions won't trap. And so there's no way for the VMM to find out. So we'll talk about how these are solved later, but these are some of the challenges which are there. Similarly, there are things around incorrect execution when you run. So I mean, things like load access rights, load segment limits, and all these things, you can actually run them and see things which again can be confusing to an operating system. So VRR and VRW basically verify some of the registers, the segment registers, and you can face issues when you run some of them. I talked about excessive faulting and ring aliasing, ring compression, and segment reversibility issue. So segment reversibility issue on context switch is the one which I talked about, where the processor has a cache state of the segment. So the segment is considered irreversible basically when it's written to. I mean, if somebody has written to it, I think you lose that track except it's in the processor cache. And so the VMM has to maintain the fact that the segment has become irreversible because of a write to a particular descriptor. So these are kind of the challenges which are there in x86 virtualization. And I think next we'll look at how these were solved with software and hardware.